All right, so let me start. I had a quick sort of thought that I will go ahead and um, start a new video so that you can find this quickly. So what we're going to be doing is taking the Arrhenius equation to make a new equation. And then we'll use that equation to solve the problem that we just did using linear regression. And this is actually like a little bit more useful to you in the sense that you can really whip this out on a test and do it. Okay? So I thought I'd make this short video by itself. It's not quite that short, but I'll make a short video by itself. So I'm going to take the Arrhenius equation and I'm going to represent it at two different temperatures. And the way I'm going to do that is I'm going to say I have ln K2 that goes with T1. I have K2, right, that goes with T1. And then what I'm going to do is subtract the equations. And this is actually kind of a standard practice kind of thing in physical sciences when you have variables that you don't really want to deal with. You know the variable ln A is the same for both. It's not really that useful of information for trying to find the rate constant. And so we just sort of eliminate it by using this equation. So when I subtract these two, actually what I mean is I'm going to take the difference of two equations, right? This is ln K2 minus ln K1. And I like doing it this way because, you know, when we do delta T or anything, it's always 2 minus 1, final minus initial, that kind of thing. And so, but in the middle, it becomes this. And I'm subtracting the two equations from each other. Now, because I'm subtracting the second equation from the first one, I changed the signs here because of the subtraction. But you'll notice what's happening with the ln of a's. They're going to cancel out. So this middle part, right, just becomes minus EA over RT2 plus EA over RT1. And then from that, I can factor out the minus EA over R, and I get this. Okay? So now, oh, I think I just wrote on top of that. Let me erase some of this so you can actually see it. But that's actually the middle part of the process. That gives us this equation. And this is known as the two-point Arrhenius equation. And it's the version of the equation that people often use to quickly solve for an activation energy if they don't want to graph the whole thing. Or if you only have 2 points, it's going to yield the same result. Okay. So back to the original data set and my equation, right? What I'm going to do is I'm going to go ahead and pick this one as T1, and this is T2. And there's a lot of room here, so I can write actually the Kelvin temperature. And this is ln 1, and this is ln2. Or sorry, K1 and K2. This will be my K1, this will be my K2. So I need the temperature in Kelvin, so what I'm going to have to do is I'm going to have to calculate for that. So let me grab a calculator here and write these values down, and you can do it as well. In fact, I'll pause it so that you can. Okay, so those are the Kelvin temperatures. Now what I'm going to do is do something that goes kind of counter what you're taught how to do in math. Only because the numbers in these calculations are pretty hard to follow precisely. Okay, so I'm going to go ahead and write out everything I have, and then I'm going to do the calculation. But I'm not going to solve the equation first. Normally you solve the equation. I just want you to see how much this simplifies the process. Okay, so I have ln, and then I need my K2, so that's this value, 3.16 times 10 to the minus third, divided by 2.52 times 10 to the minus fifth. So that's a minus 3 and a minus 5. Now what we're going to do, right, is we're going to go ahead and say that's equal to minus EA over R, and we're going to write in 1 over T2. Now T2 is 1 over 524.35 minus 1 over 462.85. And these are both in units of Kelvin, so this will come out in units of 1 over Kelvin. So now what I'm going to do is I'm going to calculate this part, and then I'll calculate this part. And then we'll solve the equation once we've done that. Okay, so let's go ahead and pull the calculator up. So, PEMDAS, 3.16 times 10 to the negative third. And then we're going to divide that by 2.52 times 10 to the negative fifth. Make sure I'm doing the math right. 2.52, 3.16. Yeah, good. It equals, and now we're going to take the natural log of that number. So that's going to come out to 4.83148, right? So I'm going to write this down, 4.83148. Did I even remember that right? I already forgot if I did that right. 4.83148. Yeah. And I'll talk a little bit about sig figs. We usually don't deal with that until later in the semester, but sig figs and logs is an important thing to keep track of. And then we're going to say equals minus EA over R, right, times whatever this is going to come out to be. And this is where students have problems with precision in calculations. Now, it's in particular what I want to show you how I deal with it, okay? So what I'm going to do is go 524.35, and then I'm going to inverse it, right? And I'm going to subtract 462.85, and then I'm going to inverse it. Now, the reason I'm telling you to do it this way is oftentimes people round the inverses of these numbers too much, just because it's inconvenient. Then I'll hit equal. And it's 2.534 times 10 to the minus 4, but negative. So 2.534 times 10 to the minus 4 kelvins to the minus 1, right? But negative. Now the negatives will cancel, so I'll go ahead and do that now, like that. And then I will rearrange this equation. So I'll be dividing by this number and then multiplying by that number on the 4.38148, okay? So EA, remember my activation energy when I did it with linear regression was 158,000. So EA is equal to, again, I have to pull my calculator out. So I have this number already, right? That's this value here. So I'm just going to store that into my calculator. I hope that works. And then what I'm going to do is go 4. That's not 4, is it? 4.83148 divided by that number times 8.314. I'm crossing my fingers, 158,517. Now, it's positive. I know on the calculator it said it was negative, but I didn't cancel the negative sign here in the calculator. I just did it. So I should have changed the sign in the calculation. The units will be joules per mole, just like it was before, because the per mole here and the per mole in here will end up canceling out with each other. Okay. All right. So I got exactly the same number in kilojoules per mole. It would be 159 kilojoules per mole. I had 3 sig figs in my original number, so then I would use that to dictate. Now, I should point out, in logs of numbers, everything to the right of the decimal point would count as the sig figs. So if it had 3 significant figures, that's actually the last significant figure. We never consider the number to the left. But if you're thinking in terms of the big picture, go back to the original data. You can't have more sig figs than that. Okay. Now, having gotten this number, what if you wanted to know the value for A, right? Then what you would do is you would go back to this equation and plug everything in. You have EA, you have R, you'll have a temperature and a rate constant, so now you can solve it for A. So that's how you use the 2-point Arrhenius equation, right, to solve for an activation energy. Okay, so the next part of this problem really is looking at how you find a rate constant at a given temperature. So the temperature in this example is 430 degrees Kelvin. And I don't even remember where the text for the problem is. I think it's way back at the beginning when we looked at the data. But we want to find k, right, at 430. So how do you do it? So what you have to do is take, again, if you're going to use the Arrhenius two-point equation, then what you have to do is take the Arrhenius equation, and typically this one will solve it for k2, right? And remember, the way this equation started, it's ln of k2 over k1, which is the same as ln of k2 minus ln of k1, like that. And then you just add ln k1 to both sides, and then you end up with this equation. Now, the one thing that's different about this equation, and this is how your textbook likes to show it, although it confuses me, to be honest with you, they just said 1 over t1 minus 1 over t2 because they distributed the negative sign in, but it's exactly the same equation, okay? Now, in order to solve the equation, you need to know the activation energy, so the 158,000 joules per mole. You have to have R, so that's plugged in, and then you have to do this. And you would do that like I showed you on the calculator. Just take the number, do the inverse, and subtract the number, and then take the inverse, and then subtract, right? And then you're going to add the log of that. Okay, so what is that, right? That is the rate constant at that temperature. So in order to use the two-point equation to find the rate constant at another temperature, you have to have one rate constant, the temperature, right? You need two temperatures really, but you need the temperature for that rate constant, and you need to know the activation energy. There we go. Sorry, like moving down. Yeah, so those are the three things you'll need to know in order to do this. You need to know this. You need to know this, the rate constant at one temperature, and that would be that temperature there. And then you plug in the temperature, the 430 Kelvin in this case that we're asking for the rate constant at, and then you solve that equation. Now, when you solve it, you're going to get this, right? That whole long mess on the right-hand side. And that's actually the log of the value, so you have to anti-log. So the anti-log is e to the ln k2 is equal to e to the minus 13.73, like that, and that will give you k is equal to, and this gives you that number there, okay? So, just really quick about how we did these calculations. The first way was linear regression. It just kind of spits numbers out at you. That was where that 430 Kelvin was at. If you use the two-point method, you get a number that's reasonably close. It's, only a little bit off, a little percentage off of the answer by linear regression. Question is, which one's better? Well, it kind of depends on your needs and the precision that you need. But in general, linear regression is a better method because it takes into account all of the data points. There's more said about this in my typed notes, right? Like which is better. But I think in general, if you can use all your data points, you're better off than just using two.